Hello, everyone, and welcome to the G2M Research webinar on storage architectures that maximize the performance of HPC clusters. I'm Mike Human. I'll be your host for this webinar, and joining us will be Kioxia, NVIDIA, and Weka. Let's go through some of the agenda and the ground rules. So I'll give a quick introduction to the topics, then each of the sponsoring vendors will present for about roughly 8 minutes. Then we'll have 3 panel questions that will kind of do round robin across the 3 panelists. We'll also have a couple audience survey questions, and at the end we'll do an audience Q&A. If you have any questions, please put them in the Zoom Q&A window. We'll hold them till the end, but then we'll go ahead and answer them. Any questions, fine, so don't feel shy. We are also going to be recording this webinar, and we'll make that recording available to everybody that registered roughly 2 days after, so be looking sometime before close of business on Thursday, getting a link to the recording as well as a PDF of the slide set. So again, kind of looking at high performance computing. So really, if you think about HPC, it originally started out largely in the defense and research areas of the world. So think of universities and government agencies. A lot of stuff in particle physics, fluid dynamics, nuclear weapons modeling and research, and aerospace. Those are some of the biggest users, and obviously things like the space program. What we've seen, though, over the past several years is the footprint of HPC is being applied in a lot of new areas in commercial enterprises, including product modeling as those capabilities have become more widespread. Business intelligence is another one, using it to see what customers are doing. And then lastly, getting into artificial intelligence and machine learning. So those are all areas that have kind of acted as a toehold for HPC into the commercial space and the enterprise. As you can imagine, there's a lot of differences between enterprise data center architectures and HPC architectures. If you think of the conventional data center, they're built to really simplify the job of the IT people, especially private clouds and things like that. They're looking for flexibility and scalability, so virtualized is really important. Being able to migrate storage and compute throughout the data center is really critical. Data integrity, making sure you don't lose data. Performance generally, while it can be important, is kind of secondary to the flexibility and data integrity. You'll see some architectures are optimized for performance, things like data lakes and things like that, but largely the enterprise is mainly built around reliability more than probably performance. HPC architectures are kind of exactly the opposite of that. You might have thousands or hundreds of thousands of processors and GPUs that are drawing data from a single storage pool. They tend to be run as projects or batches where you set up a job, you run it, and then you tear it down at the end of that. Because of that, you want architectures that are highly performant. They don't necessarily have to be standard. As long as you can reconfigure it to what you want, run your jobs, and then tear it down and wait for the next job. The challenges of moving HPC in enterprise, obviously from the IT staff perspective, you have to think very differently about how you do HPC. You also have to plan differently and manage your resources differently. And in the end, you have to execute differently because this is a very different environment. The panelists we have here today are going to help us understand some of those differences and kind of walk through it. So we have Matt Hallberg. Matt's the Senior Product Marketing Manager from Kioxia. We have Reggie Reynolds, who's the Principal Product Marketing Manager for Storage at NVIDIA. We have Joel Kaufman, who's the Technical Marketing Manager at Weka. And again, I'm Mike Human. I'm the Managing Partner of G2M Research. And so with that, let me hand it off to Matt. Matt, go ahead and take it away.
Good morning, everybody. And let me just start off by saying thank you for joining. I'm always happy to offer up some of my expertise and interact with everybody who's got questions on subject matter. So I wanted to start today with a brief overview of HPC architecture. This is probably no news to anybody, but I like to just sort of set a base before moving forward. As Mike touched on in his opening statements, HPC is indeed built differently. Nothing in an HPC architecture is general purpose. Everything has a specific purpose. So for HPC, you've got 3 main components, and a 4th would be software. And I'll let my friends at Weka talk about that. But at the network layer, you want to make sure your network is the lowest latency and the highest amount of performance possible. You got to keep data chugging between all the different clusters as quickly and as quickly as possible. Compute is, kind of where you want to show off the biggest and baddest amount of computations possible. And on the storage side, this is where you're basically storing and preparing the data for the compute nodes. But what we've seen over history is that this has been an afterthought. And I'm going to attempt to answer why and why it should no longer be an afterthought. And then, at a high level, HPC enables many different applications in the research arena, medical, et cetera, media, doing compression, doing upscaling, all sorts of things like that. Resources, so like oil and gas, manufacturing, making your manufacturing flow much faster, getting rid of manufacturing and shipping inefficiencies. And lastly, AI, ML, and deep learning. This is a diagram here on the right that sort of shows what a compute cluster and a network and a storage cluster would look like. So inside of a compute cluster, you'd have your compute nodes with several GPUs that are all attached through the CPU, which heads out to a couple SSDs, hopefully SSDs that are local storage, and then either through a NIC or an HCA, host card adapter for InfiniBand. On the network side, what we see primarily is OmniBand, OmniPath, InfiniBand, and Rocky V2 via Ethernet. And on the storage cluster side, that's just generally where you have your data lake and lots of storage out there. So not just SSDs, but there are HDDs as well, depending on how you have your storage clusters set up. Next slide, please. So I touched on this just a minute or two ago. The local storage and storage overall is sort of an afterthought. And with the advent of NVMe into the market, more and more offerings starting to be available in the market, we're seeing adoption of NVMe SSDs on the rise. And I just wanted to touch on why local storage inside of the compute node matters. For one of the particular workloads of a compute node is, during the training phase of machine learning, that happens to be one of the most resource intensive set of operations. The data sets that are out there are growing at a fast pace. And as an example, MRIs can reach multiple terabytes per image, and training sets can be composed of thousands of images. We actually released a press release and a white paper with Harvard and a couple other companies and universities where we showcased doing splices of a mouse's brain. And we've done previous ones of fruit fry brains. And what we were seeing is these MRIs of the brains were terabytes of data. And again, thousands and thousands of terabytes means you need your storage deployments to be in the petabytes. And so inside of the compute node itself, the SSDs, you want to have a good size of SSD. You want the local storage to be able to handle the reads and writes, not only from, locating from the GPUs, which is through the CPU and DRAM, or through GPU direct with Magnum IO from NVIDIA. You also want to make sure that you're handling the data coming in from the data lake as quickly as possible. So for PCIe Gen 4, the SSDs have very noticeable benefits over PCIe Gen 3 SSDs. On the sequential side, you're able to get around 7,000 megabytes per second on reads, up to 4,200 megabytes per second on writes. And for random workloads, we're talking about 1 million plus IOPS per SSD. So, I've been in the industry long enough to remember when system vendors were sending out press releases that their boxes were able to do 1 million IOPS. And now you have local storage inside of a box that's able to do 1 million IOPS on its own. And then on random writes, which aren't typically, used in most workloads, you're still seeing 70K to, there's drives out there that are in the 300K IOPS on random writes. PCIe Gen 4 SSDs are also able to take advantage of the newest 3D NAND's higher densities, which, for us, we offer a 30 terabyte drive and a 2.5 inch, 15 millimeter SSD. So a lot of capacity in a small package. Next slide, please. On the remote storage side, or the data lake, there's, and the gentlemen after me are going to talk about this quite a bit, but networking speeds, technologies, and topologies have greatly advanced over the past few years. We've seen the advent of 200 gig NICs. We've seen a lot of proliferation of 100 gig NICs. There's data points out there for 400 gig plus NICs. There's been a lot of deployments for Rocky V2, or otherwise known as RDMA over Converged Ethernet. And the NVMe over Fabrics deployments have started to pick up as well. These are all things that allow for very fast transport between your compute nodes and your storage nodes. So as I mentioned previously, the data sets themselves are comprised of thousands of files, all which need to be sent and received to and from the compute node during, to minimize the downtime. And the storage behind NICs or the HCAs should be optimized for sequential performance to send data for processing and receiving the processed data. So like checkpoints, et cetera. The faster you can offload the data from the compute node, the faster the local storage can send the data to the GPUs. And in general with HPC and with compute nodes, you always want to keep your GPUs busy because GPUs are not cheap, and anytime they're idle, you're losing out on your investment. We've seen NVMe over Fabric deployments show their strength in this by improving the performance and reducing the latency versus other like if you're using standard Ethernet or TCP over TCP, sorry. Using NVMe SSDs for staging warm data versus cold data, which would be cheaper storage like hard drives, should optimize the spend on remote storage. So you'd have hard drives, you could do hybrid AFAs or hybrid flash arrays with hard drives and SSDs, or, as a trend, the SSD price has been coming down by quite a bit compared to, let's say, a couple of years ago. Lastly, with this, you can take advantage of GPU Direct technology. GPU Direct technology is able to allows the GPUs within a system, the NVIDIA GPUs, to talk directly to the NICs inside of the compute nodes, bypassing the CPU and DRAM. And that allows them to go directly over to the storage nodes and get what they need from the remote NVMe SSDs. Next slide, please. This is just a brief demo that we did with Microsoft and a couple other companies at Ignite in 2019. And 2019 may seem dated, but we were one of the first drives to market for PCIe Gen 4, and we were able to showcase the performance difference in just doing reads across two systems running an Azure stack. So, we more than doubled the bandwidth that they were seeing internally at Microsoft. Okay, next slide. And there's more to come, right? So we've been in the news a bit, along with a couple other companies, promoting something called Ethernet Bunch of Flash, or EBOF, over NVMe over Fabric. So there is another type of storage appliance that's on the horizon. It's called Ethernet Bunch of Flash. It's meant to be sort of a replacement to JBOFs, or just a bunch of flash. This utilizes the already proven performance gains, the latency reductions of NVMe over Fabric and Rocky V2. Essentially, the SSDs that are NVMe will now have an Ethernet connection through SFF 9639, and offering 2 ports of 25 gig Ethernet via Rocky V2. What that does at the, let's say like the storage level, the storage cluster level, is you no longer have a need for CPU or DRAM, which allows for direct access to storage. So the drives just appear on your network, depending on how you have it set up, which avoids the bounce buffer of data needing to cycle through the CPU and DRAM during the offload to storage. There's a bunch of other benefits towards moving towards EBOFs. Again, you're removing cost by getting rid of the CPU, the DRAM, the NIC, HBAs. You're only cooling SSDs and the components inside. So if you were to take a box that had 24 SSDs, 24 times 18 is 432 watts. So you could have 2 500 watt or 450 watt PSUs, which is a lot less to power and cool. And then EBOF would be a great application for software-defined storage for GPU Direct or Magnum IO, again, with GPU Direct allowing access to the NICs directly, and then you'd go NIC directly to the drives. Current proof of concept for EBOPs out there is a 2U chassis with up to 24 drives. We're seeing 830K IOPS per drive, 20 million IOPS per 24 base system. And let's keep moving. I don't want to take up too much time. And then the last couple slides are just a little bit about what we've been doing. So our drives started shipping, our PCIe Gen 4 drives, CM6 and CD6, started shipping in February this past year. So we've been out there for a year now. Performance numbers here listed are PCIe Gen 4. My favorite things to look at, of course, are all of the specifications, but I'm really excited about the sequential write and the random read performance of the drives. And then the random writes, especially for 3 drive writes per day, it's a lot of performance in an SSD. And then, like I said, 30 terabytes for any of you who are looking for maximizing the amount of capacity while reducing the number of systems in a rack. Next slide, please. And then there's CD6. This is our single port SSD. The CM6 was single and dual port in the same SKU for HA, everything else. This is single port. This is more tailored towards companies that are looking to get into NVMe without having to make the giant, I wouldn't say it's giant, but having to making the cost decision, right? There's generally been a good premium between SATA, SAS, and NVMe. The CD6 series is attempting to bridge that cost gap, the premium gap, by offering really great performance, especially compared to a SATA SSD, and suitable for generally all applications. But again, it's a great way to get into NVMe without having to go all in. All right, I think that is what I brought today, and I will turn it over to Mike.
Thank you very much, Matt. That was a great presentation. Next up is Reggie Reynolds. Reggie, again, is Principal Product Marketing Manager for Storage at NVIDIA. Reggie, go ahead and take it away.
All righty, thanks, and hello everyone, and thanks for joining. And thank you, and Mike, for inviting me here to speak at this webinar. And let's just get right to it. So next slide, please. Yeah, so years ago, technical computing mostly consisted of first principle simulations and basic visualizations in a central facility. Today, researchers are merging traditional simulations with deep learning, big data analytics, and edge computing to the central supercomputer. It's the newest trend of what I refer to as data-driven scientific computing. Now, all of these workloads from data, analytics, simulation, AI, and even storage rely heavily on the networking layer to meet latency thresholds. Next slide, please. So at a high level, some fundamentals of InfiniBand. So InfiniBand remains the most efficient way to move data using the fundamental concepts of RDMA to do direct data placement into the user space, having no need for CPU or operating systems involvement, therefore delivering the highest performance and return on investment at any scale. By bringing additional network engines and capabilities closer to memory and offloading more tasks from the compute and onto the network, we now have a smarter, more capable, and the most efficient network solution that can participate in application runtime. InfiniBand is the optimal and ultimate software-defined network, and it comes complete with centralized management. InfiniBand is also an open standards-based technology that has been accepted and adopted by the HPC industry, including the high-performance storage community because of its backward and forwards compatibility. Currently, NVIDIA is delivering at HDR 200 gigabits per second, and with products and solutions, and will be coming later this year, early next year, with NDR 400 gigabits per second. Next slide, please. InfiniBand provides a complete end-to-end solution to include appliances such as the Metro X2 long-haul InfiniBand switch that can connect your InfiniBand storage solution to data centers up to 40 kilometers apart. Along with that, there's the ConnectX Smart NICs InfiniBand adapters that are RDMA optimized and support in-network computing, plus storage, cloud, and security offloads. We also have the Bluefield Data Processing Unit, or what's called the DPU, that provides high-performance programmable networking engine coupled with ARM CPUs to enable the customization and optimization of both control and data path operations. Along with the DPU, there's an NVIDIA software development kit that enables developers to easily create high-performance software-defined accelerated services leveraging industry standard APIs for storage. Then there's the Quantum InfiniBand switches, which deliver a complete chassis and fabric management solution to build cost-effective and scalable switch fabrics, ranging from small clusters up to thousands of nodes, reducing operational costs and infrastructure complexity. Advanced features such as adaptive routing, congestion control, and enhanced quality of service ensure that you get the maximum fabric performance under all types of traffic conditions. And lastly, the LinkX cables provide industry-low bit error rates, lower latency, and lower power for superior connectivity. Next slide, please. InfiniBand is driving the most successful outcomes on the best high-performing platforms with a full stack of accelerating AI, HPC, and storage, while delivering the highest throughput and lowest latency, along with providing seamless integration via Skyway to external network fabrics. Next slide, please. InfiniBand is the preferred interconnect between HPC and AI and storage infrastructures for most of the top 500 supercomputers. Noted here also is the NVIDIA Selene featuring the NVIDIA DGX A100 and the NVIDIA HDR 200 gigabits per second InfiniBand solution that is utilizing InfiniBand for both the interconnect and the storage fabric. By the way, Selene is the number five on the top 500 supercomputer list. And next slide, please. As AI, HPC, and data analytics data sets continue to increase in size, the time spent loading data begins to impact application performance. Fast GPUs are increasingly starved by slow I/O. To compensate that, GPU direct storage enables a direct path between local or remote storage. This is something that Matt touched on as well, such as NVMe or NVMe over fabric in GPU memory. It avoids extra copies through a bounce buffer in the CPU memory, enabling a direct memory access engine near the NIC or storage to move data on a direct data path into or out of GPU memory, all without burdening the CPU. Next slide, please. With the Bluefield DPU, it includes a feature called NVMe Software-Defined Network Accelerated Processing, or SNAP, as the acronym. SNAP is delivered as part of the NVIDIA Bluefield DPU's software library. It allows customers to compose remote server-attached NVMe flash storage and provide access to it as if it were local. It makes use of existing NVMe interfaces to give customers the composability and flexibility of network flash storage, combined with the advantages of local SSD performance, management, and software transparency. The ARM port processes in combination with SNAP can be used to accelerate distributed file systems, compression, data protection, and validation such as T10 diff, and many other applications. Next slide, please. Lastly, in summary, NVIDIA's InfiniBand is built as a solution. So in a real world environment, is really about all of the features and capabilities and years of experience combined that makes InfiniBand, with this complementary set of hardware components and software libraries, the most popular interconnect for storage in cloud native HPC and AI data centers. And with that, Mike, I'm gonna pass that back over to you. Thank you very much.
Thanks, Reggie. That was an excellent presentation. And last but not least, Joel Kaufman, Technical Marketing Manager at WECA. Joel, go ahead and take it on.
Hey, thanks a lot, Mike. Appreciate it. We're going to take this a slightly different direction, guys. In a nutshell, data at scale has an absolutely big problem. And what it boils down to is that when you deal with very large data lakes, very large amounts of data structures, you're going to need big compute, big networking, and big storage to help get you to that time to value that's going to be needed in HPC environments. Next slide. So what WECA did last year is we did a survey, about 500, give or take, IT professionals, data scientists, engineers, et cetera. And one of the really interesting things that came out of this was how the data varied between all these different industries. And we took a look at kind of like the top 5 or 6 here, but the generation of data from different sources flows into how all this is going to be used in an HPC environment. And it kind of leads to the crux of the problem that we're trying to solve here. It's estimated that this year, there will be 135 zettabytes of data are going to be generated this year. So think about that. That's 135 million petabytes of data. And while only some of it's really going to be used long-term, all of it will need to be processed somehow. And that's the big problem that we're trying to solve to. Next slide. Mike, if you could just click through and build this slide out, please. Thank you. So with all the data coming from these various sources, the next challenge you have in an HPC environment is that the I/O patterns are going to vary pretty dramatically across all these different workload types. Not only can it vary from small to really large file sizes, but the patterns themselves are dramatically different. For example, oil and gas during exploration will do massive readouts of large files in a big streaming mechanism because they're trying to bring in all this exploratory data based on sensor streams. But financial analysis teams, they'll do things like really bursty read writes on relatively small files, real-time analytics, that types of things. In fact, in some cases, they'll do it on a per minute basis or even less. And so they're trying to drive all that. For any IT infrastructure, this turns into an absolute nightmare because most storage systems as designed are good really at only 1, maybe 2 types of I/O, such as sequential reads or some random writes or things like that. And what they really hate is a whole bunch of different I/O patterns being thrown at them. Next slide. So I think the illustration that I want to bring to the table here is that this is a compound issue. The scale of HPC workloads is really, really daunting. I think it was mentioned earlier by Matt saying, hey, he's got some people doing MRIs and they're generating terabyte-sized files and thousands of them. Well, I'm gonna one-up him a little bit farther. We're working with a couple of automotive manufacturers today, and both on the manufacturing line, as well as the types of work that they're doing around things like self-driving vehicles, et cetera, they're generating tens of terabytes per hour and tens of millions of files a day to the point where every single month they're generating multi-petabytes of data. And it's growing. I mean, to the point where they do not throw it away. In fact, until all that data goes through a complete ETL process, right? Extract, transform, and load, nobody gets rid of it. Again, I'll use financials as an indication. They do ETL conformance and data conditioning almost in real time as much as possible based on market data in the stock market for trading desks. So it's incredibly powerful. The need to get that high performance is really there. But because of this difference in both sizes and I/O types, it exposes a situation where the storage really needs to be good at handling both high bandwidth and lots of IOPS for metadata in order to feed the compute that's available. We've reached the point where exabyte systems are already here, and they're becoming even more common. And the reason for it's pretty simple. As we've seen, the more data you can feed in, the more accurate your outcome will be. Andrew Ng, he's a really respected scientist in the AI space. He articulated it pretty well. The accuracy of your model and the accuracy of your outcome is directly related to the amount of the training data and the modeling data you can put into the system. The more data you have, the better accuracy you have. The larger, in this case for AI, your neural networks are, the better your trading models are, et cetera. And this again has that impact on your infrastructure, because if you have more data, you need more processing, you need more network, and so on and so forth in order to run those models. And it becomes this cycle of everything getting bigger and bigger a little bit. Next slide. Oops, there we go. Thank you. So let's talk about, yeah, there we go. Thanks, Mike. Let's talk about some of the challenges that HPC has brought in on the compute side a little bit. And this is really what I call the densification of compute. So if you look at what the HPC computing world has looked like for about the last 20 odd years, it was based on massive amounts of parallelism. It was based on having hundreds or even thousands of CPU-based servers, but each with, by today's standard, relatively low performing CPUs and networking. We had hundreds of low bandwidth network connections. Now, let me be very clear about this. The definition of low performance is extraordinarily relative here, right? It's CPU is in comparison to most modern GPUs, networking of 10 gig TCP/IP and less compared to the modern 100, 200, and forthcoming 400 gig types of connections that were available to get, right? But because of this, no one server in that cluster was particularly demanding on your storage infrastructure, because it was the cumulative power of all of that servers that provided performance. So pan forward a little bit, and NVIDIA now introduces the GPU to our world. And when you look what they've done, they've basically shrunk about 100 times more compute and about 40 times more networking than you get in a traditional HPC server into this one little box. And once you get that machine that's that massively powerful and can process that much data, how do you get all the data into the machine? Okay, current NAS solutions struggle because they're doing things like single-threaded I/O, which was great for distributed compute, right? You could send a thread to each one of those CPUs that were broken out, you'd be fine. But nowadays, you can't. If you throw that single thread to a massively compact DGX with all of that power, you're going to leave a ton of I/O on the table that can't be processed or can't be served fast enough. And so the result is that it leads to longer process times and a really inefficient infrastructure. We've seen a number of customers who have tried to use existing NAS solutions to do this type of work, and they wind up only working the DGX A100s at about 50% utilization. If it costs 100 grand, you just left 50 grand worth of your infrastructure on the table. So not a great place to be. Please click to the next slide. So what does Weka do in this particular case? So we've solved this problem to a large extent. And Matt talked about it a little bit earlier. As you get into NVMe drives, you can generate higher and higher performance. But instead of addressing each drive individually, basically what you're doing now is you're saying, hey, let's go ahead and combine all these, just gang all these NVMe drives together. Let's put a storage OS around it, in this case, Weka FS or Weka file system. And you can now aggregate that performance to do things that are incredible. We can saturate any 100 or 200 gigabit, in fact, multiple 100 gigabit connections across the line. We can take all of that localized storage, optimize it, and deliver, as you can see, millions and millions of IOPS in real world conditions. By the way, this is a benchmark that we did with NVIDIA to showcase how well we worked in that environment. In fact, I do have to do a little bit of a mea culpa. We actually misconfigured our benchmark, as you can see in the lower graph. And so we actually wound up accidentally limiting our bandwidth going into the system. If we had correctly flipped the switch on it, it actually would have been about 150 gigabytes per second. You should see an update to this a little bit later this year where we'll show a much bigger number across the board. But one of the things we've done is very similar to what Reggie was talking about with the cards. If you can go ahead and do things like GPU Direct, where you can go ahead and bypass the CPU and just bring I/O direct down to the GPU itself, we've done the same thing on the storage side. So instead of going ahead and saying you have to process all of your I/O using POSIX semantics at the storage array level and push it through the CPU, we are actually using something called DPDK, which is a CPU bypass and does direct I/O from the memory bus down through the system. And so similar to GDS, which is the GPU Direct system, we're able to get that same type of performance across the board. So just massive linear performance. And in fact, when it comes to linear, let me just show you. On the graph here, we only show the 4 systems. And you can see it's very linear going up and to the right. If you keep adding another system, you'll keep adding an additional, it looks like it's about 700,000 IOPS. 850,000 IOPS per system as you keep going. If you keep adding storage nodes to our system, I currently have one that is delivering approximately 350 gigabytes per second, will be expanded to terabyte per second fairly soon. And they're going to be generating somewhere on the order of 20 million IOPS across this, and it's just by adding storage nodes as they go. So ultimately, what we've demonstrated here is that we have scalability. We have the ability to take all this information and pump it into that HPC environment. The big takeaway that I really want everyone to come away with is that if you've got a data platform that you can consolidate to with best scalable performance and all the features needed to integrate with and accelerate all the data, that's going to give you a really good business outcome. And I think it's back to Michael on that.
Thank you very much. Those are some great insights, I think, especially around the idea of what bringing a DGX on board does to your workload on your network. So right now we're going to go into the panel questions and the audience surveys. Again, if you have questions, put them in the Q&A window. We will definitely answer these as we go forward. So our first question, we'll start out with Kioxia, then go to Reggie at NVIDIA, and then finally Joel at WECA. And that question is, how does storage for HPC applications differ from more traditional storage applications? I know we've kind of already answered this question, but if you guys want to throw in anything else, go for it, and let's start with Matt.
Yeah, I mean, I think I've pretty much answered it. It's just, you need to be on demand, you need to be fast, you need to be low latency. So whereas you may have been able to get away with using SATA or HDDs or even SAS to an extent, now there's much more precedence in moving forward to NVMe SSDs.
Yeah, and yeah, I think we kind of touched on this a lot, but I think from my perspective is, we just need to, HP applications, traditionally have needed to analyze and process, very large data sets. And they've been required to complete that job as quickly as possible at the lowest possible cost. And with the enterprise, and you guys touched on this when you talked about the enterprise earlier, is that, the performance wasn't really necessary or being able to worry about scale. But now with the merging of, the HPC type applications into the enterprise, the IT managers are trying to understand now how, more so now how to scale their storage infrastructure and manage the vast amounts of data and optimize that network also to connect the storage to the compute cluster for performance and and at scale, and to be able to scale.
Yeah. From our perspective, other than needing, magnitudes more performance and scale, it's not really as different as you think. What HPC applications really do, though, is they exacerbate any issues with your storage environment. For example, I mentioned a little bit earlier, but when you start to consolidate storage from multiple applications, it creates, similar like what VMware did for a long time, it creates kind of an IO blender that challenges a lot of storage systems. In the HPC space, we're starting to see a similar path happen. And because it's making things like metadata proficiency, linear scaling much more important. Like that slide that I had, which showed the verticals and the IO types on it. One of the things that we're starting to see is that each industry has an overlap of workloads within it. IoT workloads are feeding ETL processing, and then AI comes in to model the IoT data, and then it starts inferencing against other data or images and so on. And because of this blender, you're seeing this incredible amount of performance requirement needed, even for just that wide variety of HPC apps.
Very good. Let's go to the first poll question. And that question is, to what extent is your organization utilizing HPC concepts and architectures? Check one. I'm going to launch the poll and give everybody a couple of minutes to answer that. So just go to your poll window and you can go ahead and answer those questions. And while we do that, let's go ahead and jump to panel question number 2. And that question is, HPC is becoming more widespread outside of its historical home of universities, federal agencies, and aerospace. As more traditional industries utilize HPC, what key lessons do they need to keep in mind related to storage and storage infrastructure? And we'll start this time with Reggie and then go to Joel and finish up with Matt.
Yeah, thanks, Mike. So, first off, is just understanding, I think, the IO profile and workloads. And Joel, you've been hitting on this pretty heavy. And, you really have to understand what those workloads are going to look like at the storage level. Not understanding this will, it'll make it very difficult to architect an optimal storage solution for sure. And then, secondly, just having the ability to expand and scale out your storage infrastructure without losing performance or producing bottlenecks. Knowing that your storage capacity is going to grow, your performance requirements are going to increase, and technology is going to continue to advance, so that you can match storage and network infrastructure with your long-term data center strategies. And then I'll just say lastly that, just ensure that your storage and network infrastructure can be serviced, upgraded, and expanded without disruption of service. I've seen firsthand how lacking these availability requirements in your solution can really strain relationships between solution provider, customer, and end users. Thanks.
Yeah, I think Reggie hit on an awful lot of it, but ultimately flexibility and cost models are probably going to rule. The ability to start maybe in a simple way using a small, like a cloud HPC pod in AWS or something like that to quickly develop your data workflows and process small jobs is great. It's easy to set up and get going, but at some point customers are going to start to look at it and go, okay, what's the cost benefit of at scale shifting to on-site types of things, but keeping similar workflows in place, right, for efficiency of operations. That's what's going to make sense. And then other things that go into that modeling or that costing of the IT infrastructure that's needed to support this are things like, can you tier data from high performance flash maybe back to a secondary tier for less used data, and so on. So, depending what you try and do here, Weka, we can help automatically manage that, but it does require that forward thinking view of that whole infrastructure.
And just for me, Reggie and Yeah, I mean, everybody's hit on this pretty well. The key thing is, to me, is just prepare yourself for cost. It is an investment, and what are your goals? I mean, if you don't have an AI strategy by now or an HPC strategy by now, you should probably get one. Figure out if it's actually going to be beneficial to your company, and just be ready to invest. But just keep track of what your investments are and what your returns on investment are, instead of just, hey, I bought all these GPUs, I bought a compute node and everything else, and I don't know what I'm actually getting out of it. Just keep track of what you're using it for, how often it's being used, and determine if you need to make more on-prem investments, or if you need to structure some of it out to the cloud.
And I'm going to add in one thing in here, and that I think you guys really touched on it, but the fact that in the enterprise, a lot of times you're going to be doing a variety of different things with the data, whether it's ingest, whether it's pre-processing, AI, machine learning, whatever it is. One of the big differences I see between enterprise and what I'm going to call classical HPC is that migration, that pipeline of different workloads you have across the data, right? So flexibility obviously being very critical for that. And with that, let's launch poll number 2. Poll number 2 is basically, when looking at implementing HPC storage solutions, who do you look for guidance on hardware and software choices? And this is a check that all that apply. That window's open. We'll leave that open for a couple of minutes. And while we do that, let's go ahead to panel question number 3. And we'll start with Weka on this one. That question is, under what conditions does it make sense for organizations to integrate their HPC storage solutions with their general purpose storage infrastructure? Are you there, Joel?
Sorry, I was.
No worries.
I apologize. I was in the middle of typing a response to one of the Q&A panels.
No worries.
I apologize, guys. I would argue that it's already happening. In fact, I'd say it's actually happening from the opposite direction. General purpose storage is beginning to actually look a lot like HPC. Like, as I've mentioned multiple times, at scale, when you start aggregating lots of applications and I/O together, they start to form an HPC-like profile. Again, a little bit historically, people went from 100 megabit to gigabit to 10 gig, 25 gig, and sometimes 40 gig network connections. And once you start getting that performance level in a general purpose infrastructure, it's, all it takes is the next step into the fast networks, the fast GPUs, and suddenly it looks very HPC-like. One of the biggest differences, though, I think that you got to look for is that people are trying to solve a similar problem as they move in that direction of HPC, which is you don't really want to have as many silos anymore, right? There's certain reasons you want to do it for RAS characteristics, but invariably you want to get to the minimal management model where you can go ahead and try and centralize and concentrate as much compute as you can, as well as networking, as well as storage, in order to make an easy to manage infrastructure across a wide variety of applications. Once you can do that, along with things like built-in data protection and the types of things that make it reliable, that's kind of where people are going for, and those limits fall away.
Matt, what do you think on this one?
I agree 100%. For those of you who have taken a look at the popular OEMs websites, I mean, it's very easy to see that general purpose servers are opening themselves up to more and more readily available GPU options. So now you can go for example, go buy a PowerEdge 7400 system with a bunch of GPUs already attached. And as mentioned, you just want to make sure that the network around the general purpose systems that you're buying is able to actually take advantage of the GPU cluster light, I would call it. So, running 25 gig Ethernet is nice, but you want to start looking towards 100 gig and up.
Excellent. And Reggie?
Yeah, actually, when I first read this question, I had a whole different perspective on it, and then said, "Oh yeah, okay, I think I understand what the question or the ask is." And I think Matt and Joe definitely hit on it already. But I think the other part of it is, there has been a heavy investment with organizations with their Ethernet storage solutions, and so the question is there also a way to do this and to make to where it makes sense, where you don't have to you know throw that away, if you will. And with NVIDIA, we saw this a lot, and so we actually created what's called the Skyway Gateway switch, which allows you to integrate the HPC, the InfiniBand storage and the Ethernet seamlessly without and still be able to maintain all the advantages of InfiniBand as well.
Very cool. Let's quick go to the audience Q&A. We've got 3 questions in the window, and if anybody has any additional questions, feel free to put them in. The first question is, do you support fiber channel as well? Let me try to rephrase this. And I guess the real question is, does fiber channel have a role in HPC? And if so, or if not, why do you believe so? And why don't we go ahead and start with Joel, and then we can go to Matt and then Reggie on this.
Oh, yeah. In this particular case, so there was 2 questions. There was one on a different channel here, and there was one on that one that talked about fiber channel. And the answer is that WECA, we don't support fiber channel. We do things based on POSIX compliant protocol sets. But in an HPC environment, even if you go to 64 gig fiber channel, unless you're going to go NVMe over fiber over FC, something like that, it won't scale out. And so what we're seeing is that fiber channel is not the preferred connection technology for most HPC environments at this time.
Matt, what do you have to add on this one?
No, that nailed it.
Yeah.
Reggie? I expect you would say the same thing, right?
Yep. I'm right there with Joel. Right there with Joel in regards.
Yeah.
Yep.
And I will say, having been somebody who's worked at all 3 of the fiber channel HBA vendors, yeah, I would not use fiber channel for an HPC cluster. It doesn't scale, and I think, as you said, with the upcoming 200 and 400 gig networks, obviously you've got a lot more speed in both Ethernet and InfiniBand, which are probably better answers. Okay, next question we'll jump to is, can you comment on the use of converged networks for both network and storage traffic versus separate physical network hardware for storage traffic? How are InfiniBand and Rocky typically utilized together in an HPC cluster? Reggie, why don't we start with you on that one, then we'll go to Matt, then Joel.
Yeah, I think, definitely 2 totally different questions there. So we're just starting to look at converged networks at NVIDIA, and doing some preliminary testing and around that in our labs. And right now, not much to tell you in detail, other than we have been able to get it to work. It's really more about the ability to control the service levels of the jobs that are running, so that one particular application doesn't get starved out, or one particular job, if you will, doesn't get starved out. And then I don't know if I can answer in too much detail on the second question. I don't typically see InfiniBand and Roxy in the same HPC cluster. It's usually one or the other. I don't know, Joel or Matt, if you guys have seen those together, but we do have the capability of being able to access them, as separate fabrics, if you will. We do have the technology to be able to bridge those if necessary.
Yeah, our the latest Weka release, actually, we support having both InfiniBand and Ethernet into this same cluster to give you centralized storage access. But in general, though, the networks are used slightly differently. We'll use the InfiniBand for the high performance GPU side, and then for people who want to attach additional compute on the outside, maybe for different applications that they don't need an InfiniBand connection, we can offer that, but it's all connected in the same cluster with the same namespace.
And I'm a subject matter amateur, so I couldn't even answer this question.
No problem. Last question, and this one probably goes to everybody, even though it says it's focused on NVIDIA. And that question is, with the movement to disaggregated storage and servers, putting GPU outside the servers, what will the network requirements be? Is 100 gig enough, or should we expect more? Why don't we start with you on this one, Matt, and then we'll go to Joel, and then last to Reggie.
Again, I'm going to defer to Joel and Reggie. I'm not an NVIDIA stockholder, so I can comment freely that, of course, moving 100 gig is good. Go to 200, why not, right? But I'll turn it over to the expert.
Faster is always better, right?
Yeah.
Yeah. So Mohsen, the answer, at least from my standpoint, is I don't know what applications and what your needs are, but in general, if you're looking for that time to value type of thing, then you got to go with a faster network, right? 100 gig is at this point is considered, especially for NVIDIA GPUs, the DGX series. It's probably considered kind of the baseline to start with to feed it. If you don't have that, then you're literally going to let GPU cycles sit on the table, and it's going to have a lot of idle time as much as you can. So start at 100 gig. It's the bare minimum, and then work from there as you need to grow your environment.
Yeah, and to add to that, we're seeing with GPU Direct and with our DGX A100s that you can you can get up to 200 gigabytes per second at peak. So to be able to put together a network that around that, you will want to go as fast as possible, so that the the number of components that you're using to get to that to be able to exercise that that level of performance is won't be just out of hand. So I'm in agreement, Joel, that the higher your performance, of course, the better, and then of course the better you'll be able to scale out as well.
Yeah, I'll just add something to that. We go back and forth in this world, not just HPC, but enterprise computing in general, and that is, what is the slow spot, right? Is it the CPU? Is it the network? Is it the storage? Is it the operating system? Certainly if you look at things like VMware and containers, they've kind of solved the CPU utilization issue. And now with the use of GPUs extensively in HPC, it's kind of solved the CPU being the bottleneck. NVMe has done the same thing for storage and flash in general, but NVMe specifically. So I think if you look at it today, your network is almost always the bottleneck. So, whatever you can do to speed that up is usually a worthwhile investment.
Agreed.
And so with that, again, thank you for attending. As I said at the beginning, we will be sending out the slides and the link to the video. We are recording this. Expect to get those sometime before the end of the day on Thursday. Thank you again for attending, and have a great day. And thank you to our panelists, Joel, Matt, and Reggie. Appreciate it.
Everyone.
Thank you, Mike. Thank you, everyone. Take care.
Yeah, thanks a lot for having us.
Thank you very much. Have a good one, guys.
Bye-bye.